In this video, we will talk about Hess's Law. This law is named after the Swiss chemist Germain Hess, and he said that adding different chemical equations together will yield a final equation, and the enthalpy of reaction for the final equation is really just the sum of all the individual enthalpies that you've added. The way we denote this mathematically is that the enthalpy of the reaction is the sum of all of the individual enthalpy of reaction. This little funny symbol that looks like an E is called sigma, and it means the sum of. That means to add everything together. So in terms of an equation, we can say that the enthalpy of reaction is the enthalpy of reaction 1 plus the reaction enthalpy 2 plus the enthalpy of reaction 3, and so on. Hess's law allows us to determine the enthalpy of a reaction without actually performing the reaction that we want to study. We can do indirect calorimetric studies. He has two rules. If an equation is reversed, then the enthalpy of reaction is also inverted or opposite. So if it was a positive enthalpy change, it now becomes a negative enthalpy change. And if it was a negative enthalpy change at first, if you reverse the reaction, the enthalpy of reaction would now be positive. Also, if you multiply all the coefficients of the chemical equation by a constant number, constant factor, then you also need to multiply the enthalpy of reaction by that same factor. So let's look at the formation of NO2, nitrogen dioxide. The formation equation is nitrogen gas plus 2 moles of O2 yields 2 moles of NO2. And from our studies, it can be found that the enthalpy of reaction is 68 kilojoules. However, let's say that it's difficult to study this reaction directly. We can study two reactions. The first one is nitrogen plus oxygen gas yields 2NO. The enthalpy of reaction here is 180 kilojoules. And then the second reaction is 2NO plus oxygen gas yields 2NO2. The enthalpy of reaction here is negative 112 kilojoules. Notice that we can add these two equations together. Just like in math, when you can add or subtract systems of equations to get rid of terms that you don't want, we can do this with chemistry as well. If we add everything together, on the left-hand side we have N2 plus O2 plus 2NO plus O2 yields 2NO plus 2NO2. Notice that there's two NOs on the product side, on the reactant side, and 2 NOs on the product side. Therefore, we can cancel it out. We can also sum up to the like terms, NO2, to give us N2 plus 2O2 yields 2 nitrogen dioxide. Because we added these two equations, we also need to add up the enthalpy of reaction. So if we add 180 with negative 112, we will get the enthalpy of reaction. And the enthalpy of reaction here is 68 kilojoules. So this 68 kilojoules is the same as the amount that we're told. So now we've proved that by adding two different chemical equations together, we can determine the enthalpy of reaction for a third equation. And this slide just shows you the process we just did. We can see that the 2 NOs cancels out. One set of 2 NO is on the product side, and another set of NO is on the reactant side. We add everything together, and we get the enthalpy for this reaction to be 68 kilojoules. We can also express this in terms of an energy diagram. Here we have our first equation going from N2 reacting with two oxygens, giving you oxygen gas plus 2NO. In the second reaction, another O2 gas reacts with 2NO, giving you 2 nitrogen dioxides for a net enthalpy change of 68 kilojoules. We can also write in a one-step reaction when we had the nitrogen gas plus 2 oxygen gas reacting in an endothermic reaction to give you 2 nitrogen dioxides. Let's revisit a couple of the Hess Law rules that we mentioned earlier. When you reverse the direction of a reaction, in order to make your math work, you have to change the sign for the enthalpy of reaction. Here, the sign, the forward reaction is endothermic. It takes in 68 kilojoules. However, when we reverse the reaction, so now the nitrogen dioxide, instead of being a product, is now a reactant, and the nitrogen gas and the oxygen gas, instead of being a reactant, is now a product. The reverse reaction, the enthalpy change is now exothermic. It will give off 68 kilojoules for every one reaction. In terms of math, you can think of this as multiplying the first equation by -1. However, instead of being a -1 mole of nitrogen gas here, it is now, instead of a reactant, it is now a product. And the -1 also applies to the 68 kilojoules, so now this is now -68 kilojoules. The second Hess's law tells us if we multiply the balance equation by a constant factor, we have to change the enthalpy of reaction as well. We have to change it by that same constant factor. It really means that the magnitude of the enthalpy is directly proportional to the amount of chemicals present. So if we double all the chemicals present, we should double the enthalpy reaction as well. So here, if we double our original equation by 2, we multiply everything by 2, we now have 2 moles of nitrogen gas reacting with 2 times 2 moles, or 4 moles of oxygen, leaving you with 2 times 2 moles of NO2, or 4 moles of NO2. And you'll notice here that the enthalpy has also been multiplied by the constant factor of 2. So now we know the rules, let's look at an example. The key here is that we want to work backwards from the reaction of interest. So here our example is 3 moles of carbon reacting with 4 moles of hydrogen gas to produce 1 mole of propane. And we want to find the energy of formation, the molar enthalpy of formation. To find the molar enthalpy of formation, we're given 3 different reactions. We have the reaction of carbon with oxygen to yield carbon dioxide. We have the reaction of propane with oxygen to produce carbon dioxide and water. And lastly, hydrogen reacting with oxygen to produce water. We will go over one way of creating this final equation. However, you should know there's more than one correct pathways to this approach. The first thing we'll do is look at the carbon in our desired equation. Here we have 3 moles of carbon, but in this equation, in equation 1 number here, we only have 1 mole, the indivisible 1. So what we need to do is multiply the first equation by 3. And we'll do this on the next slide. So as we said before, our first reaction, our equation number 1, only has 1 mole of carbon, but we want 3, so we need to multiply this entire equation by 3. So that we have 3 moles of carbons plus 3 moles of oxygen, yielding 3 moles of carbon dioxide. The enthalpy of the reaction is now multiplied by 3, so it's now negative 1,182 kilojoules. Let's look at the second equation that we're given. We notice here that propane is on the reactant side. However, at the end of the day, we want propane to be on the product side. Therefore, we need to flip this reaction. Or you can think of it as multiplying by -1. If we do that, if we flip the equation, propane and oxygen is now on the product side, and carbon dioxide and water is now on the reactant side. We have to flip negative 2,200 kilojoules into positive 2,220 kilojoules, or again, you can think of this multiplying by -1. Looking at the two equations that we just created, we know that we can add this up right now. And when we do, we notice that the carbon dioxide from our first equation cancels out with the 3 carbon dioxide in our second equation. So that when we add this together, we just have 3 carbons reacting with 4 waters to yield a propane with 2 oxygens. The oxygen here is 2 because here we had 3 oxygens on the reactant side and 5 oxygens on the product side. However, the 3 cancels out part of the 5, leaving us only with the 2. So now we notice that in our intermediate equation, we have 3 carbons reacting with 4 waters yielding propane and 2 oxygen. And our final reaction, there is no oxygen as a product, therefore we have to somehow remove it. And we notice that in our third equation that we're given, that we can use to manipulate, we have hydrogen gas reacting with half a mole of oxygen gas, to yield water. We could easily multiply this third reaction by 4 to get 4 molecules of water to cancel it out with our intermediate stuff. And 4 times a half is 2 oxygen, and the 2 oxygen here will cancel up perfectly with the 2 oxygens here. So then we multiply our third equation by 4. We get 4 hydrogens with 2 oxygen and 4 waters. This now cancels out. The water cancels out. The oxygen also cancels out, leaving us with 3 carbons plus 4 hydrogen yields propane. And we add the enthalpies together. This 1144 is 4 times the enthalpy of reaction that we're given because we multiply everything by 4. And we add it up with our intermediate enthalpy to get negative 106 kilojoules. Now remember, this is only one possible pathway to find a final solution. There are alternate pathways as well, and as long as you have the final equation that you want, any method that you can come to achieve this is fine. Here on the last slide, let's summarize all the rules for Hess's Law problem solving. Determine enthalpy change for reacting using Hess's Law. We have first to write the net equation, if we're not told what it is. And then we have to somehow manipulate the given equations so that they will add up to yield the final equations. Remember, you can multiply or divide by a constant factor, or even reverse the sign of the enthalpy change simply by flipping the products and the reactants. Lastly, or next, is to cancel out and add all the remaining reactants and the products, and then add the component enthalpy change to obtain a net enthalpy change. And then lastly, if you're asked to do so, calculate the molar enthalpy for the reactant or for a product. Remember, molar enthalpy is denoted as delta HM. This really means in the units of kilojoules per mole. Hopefully these rules will help you determine Hess's Law problems.